Well, here we are. You want to know all about calculus in the span of an hour or two or three? Well, I gotcha. This is the Calculus 1 crash course. We go over all the very important things about calculus in the span of one video. I don't know how long it's going to take, but I've got like 40-some slides to deal with, so it should be interesting. Should be interesting for sure. So, I don't know what this thing is, but I have to move it. Move it. Ooh, okay. What is a derivative? The derivative is the first main component to calculus. We talk about limits, which transitions into the concept of the derivative. The derivative gives us the slope of a tangent line at a given point. Or in this case, the way I word it is the slope of a curve at a given moment, aka the slope of the tangent line. Another word for slope that you learned back in Algebra 1 is rate of change. So if you're talking about just a regular old line, like this, I'll draw it out, and I say, hey, find the slope of a tangent line at a specific point. Well, if this is my line, and we care about the point being, I don't know, here, then the slope of the tangent line is going to be the slope of whatever that blue line is right there. However, when we talk about real life examples, like you have a particle and it's got a position, then the derivative is going to give us velocity. Or if maybe you're talking about a tank of water, the derivative could give us gallons per minute. Here's a few other examples. So the derivative gives us the slope, which is a rate. So that's what the derivative gives us. Okay, move that to that. So here are the typical derivatives. The derivative of a constant is 0. Okay, that's what this guy is saying. What this guy is saying is if I take the derivative of x to the whatever power, you drop down the n and take away 1 from the n. That's what 2 is saying. Of course, if there's already a coefficient attached to it, whatever you drop down gets multiplied to the coefficient. The derivative of e to the x is e to the x. The derivative of ln of x is 1 over x, also worded as x to the negative 1. The derivative of sine is cosine. The derivative of cosine is negative sine. And the one thing that I don't have here is the derivative of tangent is secant squared x. So let me quick write that out. Secant squared x. Okay. So those are the main ones that you're going to want memorized. So let's put that into practice. These are just tricky problems. All the problems that we're going to look at in this crash course is going to be medium to difficult difficulty. They're not basic problems. So we're going to have to take a lot of these and maybe rewrite them to make them look a little bit better. So let's look at one at a time. I'll blow this up. I'm being asked to take the derivative of that guy right there. So I like the way that that's written. Okay, I like the way that that's written. I'm going to leave that like that. Oof, that 3 looks awful. Minus, I'm going to rewrite the square root of x cubed as x to the 3 halves and leave that as that. Y prime, I could also write this out as dy dx, is going to have me bring this down and take away 1. So 6x. This is going to have me bring this down and take away 1. So 3 halves x. 3 halves minus 1 is 1 half. The coefficient stays here. And the derivative of sine is cosine. So cos x. And all I'm going to do is just rewrite this guy right here. So y prime is going to end up equaling 6x minus 3 halves root x plus 2 cosine x. Am I looking in the right direction if I go like this? Hello? Okay. Questions? I didn't think so. Nothing to rewrite here. Nothing to rewrite on this one. It's just pretty straightforward. Let's write this out as dy dx. If you're like, why is he writing? Oh boy, this stylus is just not working today. Let's keep with this big one. If you're like, why is he writing it differently? You remember, you can write out derivatives as y prime, dy dx, the ddx of stuff. It all depends on what you're given, so I'm just going to mix it up from time to time. Dy dx equals the derivative of any regular number just turns into 0. If I bring the 7 down, that's going to end up being 7 times negative 2/3 is going to be negative 14/3 because you multiply the 7 to the 2. Take away 1 from the 7. Okay, I'm going to different color it up. ln of x becomes 1 over x, so 2 times ln of x is going to be 2 times 1 over x, or in this case, 2 over x. And you don't change, because the derivative of e to the x is e to the x. So the derivative of negative 4 e to the x is negative 4 e to the x. Pretty nice. Although this problem had more components to it, it ended up being a lot friendlier. And that's what we like. Good old friendly problems. Find the line tangent to that. So we're literally taking the definition of what we saw in the second slide. I think it was the second slide. And we're applying it to here. So the line tangent means we need to come up with the equation of a line. Now, the most standard equation of a line is actually not standard form. It would be slope-intercept, which is y equals mx plus b. However, this is calculus. And I'm thinking in calculus, we could just use point-slope form, which I will write out right here as if I give you a point and a slope. So that's a slope first, and that's a point. If I give you a point and a slope, that an equation in point-slope form is going to be y minus y sub 1 equals m times the quantity x minus x sub 1. However, in calculus, we would write it out like this. Our point is going to be that x value, and we'll keep calling the point x sub 1 y sub 1. Actually, no, we won't. We'll call the point x sub 1, but I'm going to change the y sub 1. So in calculus, it might be worded out as this. Y sub 1 is achieved by taking whatever your x sub 1 is and plugging it into the original formula. I know we called this g of x, but usually we would write it out as f of x, or in this case, f of x plus 1. A book might call it f of x sub 0, whatever. That's going to equal the derivative, because slope is derivative, or derivative is slope, and then we would plug in that x sub 1 value, so m turned into that, times x minus x sub 1. This is our x sub 1. What we haven't found is the derivative, and what we haven't found is f of x sub 1, f of x sub 1, I said that right, which means we just plug in, 4. After we just plug in regular 4. Let's find the derivative first. do that by using this color. So the derivative is going to be, let me rewrite this as, let me rewrite the original as 16x to the negative 1 minus 4x to the 1/2. So the derivative is going to have me drop down the negative 1 and subtract 1 from it. So negative 16, because negative 1 times 16 is negative 16. X to the negative 1 minus 1 is negative 2. Drop down the 1/2, and half of negative 4 is negative 2. And take away 1 from a half, and you have negative 3/2. Negative 1/2, my bad. So I'll write that out. I'll rewrite that as negative 16 over x squared minus 2 over root x. And that's g prime of x. Now the slope is found. The slope is found by me taking the x value that I was given, that one, and plugging in 4. So my slope is going to be g prime of 4, which is going to equal negative 16 minus, or over 4 squared, which is negative 1, minus 2 over the square root of 4, which is also negative 1. So my slope is negative 2. So my slope is negative 2. I still have to find my other y value, and I find that by plugging 4 into the original equation. So here's the original equation. If I plug 4 in, 16 divided by 4 is going to be 4, minus 4 times the square root of 4 is going to be 4 minus 8, which is negative 4. So this guy became negative 4. We already said that this guy was positive 4. So putting this all together, I have y minus negative 4, so y plus 4, equals negative 2 times x minus 4. And you might be like, oh, well, should I distribute and subtract 4 and turn it into slope-intercept form? No need. That's an equation in point-slope form. We're done. So if I were to graph this guy, whatever that graph might look like, and it's not going to be too pleasant looking, and put a dot at 4 and say, what is the equation for a line that's tangent to this function at 4? There you have it. There you have it. So as we mentioned in that second slide, the derivative gives us slope. Slope is also called rate of change. And if I give you a position, and later on we're going to call this rectilinear motion, but let's just pretend we don't know that yet. The rate of change for a position is found by taking the derivative. So when it says determine the velocity of the object at any time t, that just means take the derivative. So I'm going to blow it up just a little bit. I'm going to take the derivative of that s of t function. So f prime of t is going to be me bringing that down and multiplying it to 3, 12, and then subtracting 1, so 12t to the third. Bringing that down and multiplying it, so negative 20 t to the second. Bringing that down and multiplying that, so plus 152, subtract 1 from 2, which is t, and then that constant becomes 9. Or 0. That constant, which is 9, becomes 0. in order to determine the velocity, we just take that 4 and plug it into that velocity function. So we're finding s prime of 4, which is going to be 12 times 4 cubed minus 120 times 4 squared plus 152 times 4. Let's see if Siri can handle all of this. 12 times 4 times 4 times 4 minus 120 times 4 times 4 plus 152 times 4.
It's negative 544.
Yeah. So this velocity is negative, which means it's going downward. I don't have any units, so I'm not going to say feet per second, meters per hour, miles per minute. I don't know, because I stole this problem from the internet. But that's my answer. Fast little bugger. So we did one just like this. So let's remind ourselves what the equation is. Point slope form is y minus y sub 1. So I'm going to change that to y minus f of, in this case, what do I have? T. So f of t sub 1 equals slope, which is the derivative. So f prime of t sub 1 times a quantity x minus, well, it's actually t, so I have to change it. T minus t sub 1. So f prime, or the derivative, y prime. Maybe I should have used y, but it's too late. Y prime is going to be, bring that down, 8t cubed, bring that down, minus 20t, get rid of that, plus 13. Okay, so the derivative, or as I like to call it, f prime of 5, because we're plugging in 5, that's our t sub 1 right there, that's our t sub 1, is going to be 8 times 5 cubed minus 20 times 5 plus 13. 8 times 5 times 5 times 5 minus 2 times 5 plus 13.
It's 1003.
So that's our slope. It's very steep. So we found u. We have u. I need u. So f of 5 is going to be me plugging this into the original function. And the original function was 2 times 5 to the 4th minus 10 times 5 squared plus 13 times 5. Two times 5 times 5 times 5 times 5 minus 10 times 5 times 5 plus 13 times 5.
That would be 1065.
I wonder if this would work. 2 times 5 to the 4th minus 10 times 5 squared plus 13 times 5.
The answer is 1065.
That's all good. So if I put it all together, y minus, we just found that out to be 1065, equals the slope, which we found out to be 1003 times t minus 5. The sunshine's really hitting my camera hard. Ew, there we are. Okay. All right, let's talk about product rule, quotient rule, and then eventually chain rule. If I give you two things that are multiplied together and I ask you to differentiate it, I ask you to take the derivative. You're going to set the first thing to u, the second thing to v, and then it's going to be u prime v plus v prime u. That's the product rule. If I ask you to take the derivative of a fraction or something divided by something else, you're always going to have the numerator, which is the top, going to be your u. The denominator will always be your v, and it'll be u prime v minus v prime u over v squared. Okay, so that's our product rule. That's our quotient rule. Let's put some of them into play. Ugh. All right, so I'm going to take the derivative of this guy. I'm not going to focus so much on simplifying because that's my goal here is not to worry about foiling and stuff like that. My goal is to understand what the rules are. So I'm just going to say, let's let u be my u and u be my v. So u prime is going to be 8t minus 1. V prime is going to be 3t squared minus 16t, not 8. Let's clear that up. Let's do this. You know what? Let me quick rewrite that over. Sorry. It's good practice anyway. All right, so that's our u. Boom. Let's use different colors. That's our v. Boom. U prime is going to be, what did I say? 8t minus 1. V prime is going to be 3t squared minus 16t plus 0. And then we put it all together. U prime v is going to be 8t minus 1. I think an angel just got its wings, by the way. U prime v. So there's my v, writing it in green. I probably should have written it in green and not actually purple. Plus v prime, which is the one in black, u. And those of you who are overachievers, oh, another angel got its wings. Those of you who are overachievers, you can FOIL stuff out and combine like terms. But, you know, that's not going to be my focus here. My focus is in making sure that we understand when to use the product rule. I had this function times that function so we could set it all up. If I were really gung-ho and wanted to do the problem, I could have FOILed this out and did a regular old derivative of a polynomial and ended up getting the same answer at the end anyway. It just looks different. But we're doing product rule for that one. This one, I'm going to rewrite it out. And we're going to do quotient rule. Now, I'm going to rewrite out one thing, and that's going to be the square root part. All right, so let me rewrite it out as x to the 1/2 plus 2x all over 7x minus 4x squared. So my u is up here. U's always in the numerator. My v is down here. U prime is going to be, bring that 1/2 down. So 1/2 u, subtract 1 from a half, so negative 1/2 plus 2. Okay. I'm looking for my, there it is. Bring the 1/2 down, take away 1, plus just take away the x. My v prime is going to be 7 minus 8x. And my v squared is going to be me just taking the entire denominator and squaring it. Again, you know, if we had all the time in the world, oh, another angel. If we had all the time in the world, what we would do is we would FOIL that out and FOIL a whole lot more, combine like terms, simplify things. But again, our focus is not necessarily on, you know, making sure we know how to simplify stuff. I know how to simplify. I'm not worried about that. I want to make sure that our focus is understanding how to and when to use those rules. So my final derivative, and I'm going to use purple again, is going to be f prime of x equals u prime v. So u prime ended up being there in black. So u prime 1/2 u to the negative 1/2. And let me, or is it x? It should be x to the negative 1/2. Not sure why I put u there. It should be x to the negative 1/2. And while I'm at it, x to the negative 1/2 is the same thing as 1 over square root of x. So I'm just going to do that. Something that you should be like, oh, yeah, I know. Plus 2, that's u prime. V was 7x minus 4x squared minus v prime, which is 7 minus 8x, u, which is, I'll rewrite it to its original form, square root of x plus 2x all over v squared, which we said was there in green. Lots of simplifying could be done, foiling, stuff like that. But yeah, we'll save that for another day. Like ever. Oh, there you are. Because I'm looking that way now. Chain rule. So chain rule is usually function within a function stuff. Sine of blah, blah, blah. Blah, blah, blah to the third power. E to the blah, blah, blah. Basically, if you can put a bunch, if it's not what we're normally used to, like e to the x, and it's e to the something else, or instead of, you know, x to the fifth, it's something else to the fifth. If that x changes, that's when we're going to use the chain rule, and we're going to treat that as the inside stuff. Now, this is the chain rule, and it looks different if I were to put like f of x and g of x and stuff like that. And that's like, what the heck is that? Well, that's basically saying if I have something like, you know, if normally I'm used to sine x, but if I have sine of 3x plus 1, just for example, I would take the derivative of the outside. The outside is sine, so the derivative of the outside is cosine. I would keep the inside and then multiply the whole thing by the derivative of the inside. So this would just end up being 3 cosine 3x plus 1. Okay? Take the derivative of the outside, keep the inside, multiply the whole thing by the derivative of the inside. So let's do some more. So I usually have e to the x. No, I don't have e to the x. I have e to the 1 minus cos x. So the outside stuff is e. The inside stuff is 1 minus cos x. So what I do is I take the derivative of the outside. Well, what's the derivative of e? E. Keep the inside, 1 minus cos x, and multiply the whole thing by the derivative of the inside. The derivative of negative cos x is negative sine x, or just sine x. So our final answer in this one, because I think it just looks better if you write it out front, is going to be sine x e to the 1 minus cos x. Ooh, that looks sloppy. But that's what it is. That's what it is. So let's do a bunch. And this is going to be a combination of everything. So let me stretch you up, zoom you up. So I'm going to take the derivative of 1. So I have one of two options here. I could FOIL that 4 times and it would be an absolute nightmare. Or I can realize, like, wait a minute, that's kind of like x to the 4th, but instead of x, I have a bunch of stuff. Chain rule. So my inside stuff is 6x squared plus 7x. My outside stuff is to the 4th. So to take the derivative of the outside stuff means to take the derivative of to the 4th. So you bring the 4 down. That 4 becomes 3. Keep the inside stuff, 6x squared plus 7x, and multiply the whole thing by the derivative of the inside stuff, which is going to be 12x plus 7. Neat. So chain rule is actually not that bad. Those of you who whined about chain rule, stop it. Quotient rule. I don't like quotient rule, but hey, we're going to get through it anyway. So I have, this is my u, this is my v. U prime is just going to be 5. V prime is just going to be 1 over x. And v squared is ln of t squared. Quotient rule. Quotient rule is u prime v minus v prime mu. So u prime is 5. V is ln of t minus v prime, which is 1 over x. So why don't I do this? U, which is 1 plus 5x. See what I did there? Is it t or is it x? Oh, it's t. So let's make that 1 over x a t. Oops. And let's make this a t too. And that's all going to be over v squared, which is ln of t squared. And we're just going to leave it like that. No need to do too much. No need to combine fractions and make the day harder than it has to be. Good job. Practice makes perfect. All right. I'm going to rewrite stuff out, and then I'll clean it up. I'm going to rewrite. I'm going to rewrite as 1 plus square root of v x cubed is going to be 3 over 2. V is going to be x to the negative 3rd minus 2 times the cube root of x is 1 over 3. U prime is the derivative of 1, which is 0. The derivative of x to the 3 halves, which means we bring down the 3 halves. We subtract 1, so I get 1 half. And v prime is the derivative of x to the negative 3rd, which means bring down a negative 3, subtract 1 from negative 3rd, which is negative 4. This is bring down the 1/3 and multiply it to -2, so -2/3, and subtract 1, which is -2/3. Tricky, tricky, tricky. So the derivative y prime is going to be u prime v. So we've got 3 halves. And instead of x to the 1/2, I'm going to make it square root of x. That's u prime. V is going to be x to the -3. You know what? I prefer that to be 1 over x cubed. Minus 2x to the 1/3. You know what? I prefer that to look like cubed root of x. Plus v prime. V prime is -3x to the -4. You know what? I'd rather have that look like -3 over x to the 4th. Minus 2/3 x to the -2/3. You know what? I'd rather have that look like this. Cube root of x squared. That's the cube root of x squared. And it's downstairs now. So that's v prime. U, which is 1, plus, you know what? I'd rather that look like the square root of x cubed. I fit that in right above my head. Ooh, it's like a TikTok. I need a song to go behind it. It's fun to stay at the you can't see it. Oh, shoot. Since I sung that song, I'm not going to make money off of this YouTube now. I'm not going to make money anyway. Unless this crash course makes me super popular. Usually I'm taking the derivative of ln of x. Well, now I'm taking the derivative of ln of stuff. So my inside stuff is 1 minus 5y squared plus y cubed. So we take the derivative of the outside, which is ln, so I get 1 over, keep the inside stuff, 1 minus 5y squared plus y cubed. Multiply the whole thing by the derivative of the inside stuff, which is going to be times, and you know what? I'll just bring it up top. Negative 10y plus 3y squared. Yeah, and that's f prime of y. It's the worst y I've ever made in my entire life. Yeah, I need new styluses or stylies. I know, I bought this because Taylor Swift sang a song that it'll never go out of style. Another tangent line, gross. Find the tangent line to f of x equals tangent x plus 3 cos x at x equals 3. Well, let's remind ourselves. Y minus f of x sub 1 equals f prime of x sub 1, x minus x sub 1. There's my x sub 1. So I need to find the derivative. So f prime is going to be secant squared x plus minus sine 9 sine x. I have to plug in pi. So I have secant squared pi minus 9 sine pi. Secant squared pi. 1. Sine pi. 0. Oof. So minus 0. So is 1. All right, so my slope is 1. To find out what my f of x sub 1 is, I have to do f of pi, which is tangent pi, plus 9 cos pi. Tangent pi. 0. Whoa, that's the worst 0 ever. Cosine pi. Minus 1. So minus 9. Which is negative 9. Negative 9. Negative 9. So I have y minus negative 9. Y plus 9 equals f prime of x, which is 1. So I don't need that 1 there. X minus pi. And again, if you're like, should I subtract 9 from both sides? Sure, but you don't have to. You don't. You don't. All right, implicit differentiation is the idea of taking the derivative when y is not all by itself, or f of x is not all by itself. It's about a 5-step process. First, you take the d dx of both sides. If you take the d dx of a y, you have to attach a dy dx. Move all the dy dx's to the left and everything else to the right. Factor out a dy dx and divide out the stuff. So I'm sure you all got that. Having said it, let's do it. So we're going to d dx both sides. D dx both sides. Anytime you take the derivative of a regular x value with respect to x, you just take the derivative like you normally would, like so. However, every time you take the derivative of a y value with respect to x, you take the derivative, but you also attach a dy dx to it. Okay, the derivative of 4 is nothing. 0. Simple. You put all the dy dx variables to the one side, usually the left, and move everything else to the right. So I'm going to subtract 2x from both sides, minus 2x. That crosses out. That leaves me with 3y squared dy dx minus equals minus 2x. Divide everything by 3y squared. Divide everything by 3y squared. That crosses out, and I'll write it up here where I have a little bit more space. Dy dx is going to be negative 2x over 3y squared. Same rules apply. I'm going to take the d dx of everything. I'm just going to write it out like this. I'm not sure if it's even math proper, but I'm doing it. When you take the d dx of both sides, you say, all right, well, anything that has a y attached to it gets that dy dx. So this becomes 6y squared dy dx plus 4, just kidding, 8x minus 1 dy dx equals 6x to the 5th. That positive 8x, I'm going to just move that over to the right and make it negative 8x. I subtract it from both sides, but if you're going to just do the opposite to both sides, I'm just going to write it out this way. No need to show every single step. And on the left side, I have 6y squared minus, I forgot my dy dx, very important. Dy dx minus dy dx. Now is time to factor out the dy dx. So that's 6y squared minus 1 equals 6x to the 5th minus 8x. Divide everything by 6y squared minus 1. And again, I'll write my answer up here. And dy dx is going to equal 6x to the 5th minus 8x over 6y squared minus 1. Well, let's zoom up. Give myself a little bit more space. There we are. So I'm going to ddx both sides. $14y dy dx plus 3 cos 3x, because it's chain rule, equals nothing, minus 4y cubed dy dx. Let's do this a little different. Well, no, I'll keep it with the dy dx on the left. That 3 cos 3x is just going to move to the right and be negative 3 cos 3x. That negative 4y cubed dy dx is going to move to the left and become positive 4y cubed dy dx. And 14y dy dx is still living strong over here all by itself. And then there's a plus sign. Factor out the dy dx. And that leaves me with 14y plus 4y cubed equals negative 3 cos 3x. Divide everything by 14y plus 14y cubed plus 4y cubed. That crosses out. And so dy dx equals negative 3 cosine 3x over 14y plus 4y cubed. I see you, implicit differentiation. I see you. Well, the nice thing here is we have our point, so all we need is the slope. So here's our point. Easy peasy. All we need is the slope. So let's ddx both sides. So I'll write that out poorly like this. ddx both sides. So that leaves me with 4x cubed plus 2y dy dx equals 0. Subtract 4x cubed from both sides. So 2y dy dx equals negative 4x cubed. Divide everything by 2y. And dy dx is going to be negative 2x cubed over 2y. Now I have to plug in my point, two of them. Why the negative square root of 2? Why? Negative 2 times x cubed. What's x? 1. So 1 over 2. Oh, why did I have that 2 there? That 2 should be gone. That 2 should be gone. My fault. That should just be y. Yeah, because that simplifies. My bad. X cubed is going to be 1 cubed, which is 1. Y is going to be negative square root of 2. So my slope ends up being 2 over root 2. Don't even think about trying to simplify. I mean, you could simplify that. If you multiply the top and the bottom by 2, would end up just being the square root of 2 would end up being square root of 2. Really? Yeah. So that's my slope. So y minus y sub 1 is going to be y plus root 2 equals root 2 is my slope, x minus x sub 1. Fun. Critical points. I'm actually going to skip this one too. Skipping a few. 1, 2, skip a few. Well, I did. I am going to do that one. Critical points. Critical points are found when your derivative is equal to 0. So a lot of times the zero product property is going to be used. A lot of times factoring is going to be used, maybe quadratic formula here or there. But that's basically what we're dealing with here. So first off, I have to take the derivative, which is 24x squared plus 162x minus 42. Set that equal to 0. Factor out a 6. Yeah. So that would be 4 x squared plus 27x minus 7. So that's going to factor out to, I'm going to put the 4 there. I'm going to put the minus there. I want to put the plus 7 there, which means you have to be a 1, which means you have to be an x, which means you have to be an x. 4x squared plus 48 minus 1. Yeah, that'll do. And so if you set that equal to 0, nothing happens. If you set that equal to 0, you would add 1, divide 4. So one of my critical points is a quarter. And if you set that next one equal to 0, you would subtract 7. So those are my critical points. We're skipping that because that one's just brutal. It's a lot of factor by grouping problem stuff. I regret putting it in there in the first place. It's just not fun. Sketch and graph the identity of the relative extrema. So using the old internet, using Desmos, I'm going to make a rough sketch of x squared minus 4x. It's going to look like this. Okay. And my job is to find the relative extrema. Not the absolute extrema, the relative extrema, which means find the maximums, find the minimums, relatively speaking. We're only going to have one, and it's going to be right there. And I probably should have moved that -5 down just a teensy bit more, which is what I just did. So first, in order to find the relative extrema, I have to find the critical points, which means you set that equal to 0, you take the derivative, gives you this, add 4, divide by 2. So my critical point happens at 2. So this guy is going to be 2. I make a sine table, or a sine graph, for the derivative. Well, actually, in this case, it's g. So let's turn that f into a g. Perfect. Magic happens at 2. So in my mind, I have to plug in something smaller than 2, 0, and something bigger than 2, 10, and see if I get a positive or a negative. And I'm plugging it into the derivative. So here was the derivative. Let's get my mouse. Here was the derivative. If I plug 0 into the derivative, I get 2 times 0, which is 0, minus 4, which is a negative number. So that's negative, which means it's decreasing all the way up to 2, which we can see that in our graph. It's decreasing all the way up to 2. If I plug in 10 into the derivative, I get 2 times 10, which is 20. 20 minus 4 is 16, which is positive. So it's increasing. So what this means is if I have something that goes from decreasing to increasing, the moment of that change, that critical point is going to be a relative minimum. So I have a relative minimum at 2. Now, if I want to find the exact point, which I'm going to do, I'm going to take that critical point of 2 and plug it into the original equation. So that would give me 2 squared, which is 4, minus 4 times 2, so 4 minus 8 is -4, and that leaves me with a relative minimum at the point 2, -4. And we can kind of see that based off of my picture. My picture, although not good, really ain't half bad. So the same exact thing, but I believe we deal with absolutes now. So I have negative, what is it, x minus 4 cubed. That's 4. Oh, it's x plus 4 cubed. That's why that didn't look right. How can I change it? Where there's a will, there's a way. That's supposed to be, I could have just erased everything, but I decided to be stubborn and do this instead. Now, I also have to keep in mind that I stop at negative 3, and I stop at negative 6. So let's find our critical point. Our critical point is found by taking the derivative and setting it equal to 0. We have chain rule here. So the derivative of the outside stuff would be me taking that 3 and moving out in front, including the negative. So I have negative 3. That 3 becomes a 2. Keep the inside stuff, x plus 4, and then multiply everything by the derivative of the inside stuff, which is 1. So times 1. If I do 0 product property and set that equal to 0, nothing happens. If I set that equal to 0, I would subtract 4 and have a double root of negative 4. So my one and only critical point happens at negative 4. So I'm going to make a sign chart. I'll plug in, I don't know, negative 10. Plug in 0. If I plug that in to the derivative, which is right here, plugging in negative 10 would be negative 10 plus 4 is, I don't know, but square it and you get a positive times a negative, so it's going to be a negative decrease, and we can see that in the picture. If I plug in 0, I get 0 plus 4, which is 16 after I square it, times negative 3 is another negative. Oh, surely I did something wrong, you ask. Well, don't call me Shirley. Airplane. And you didn't ask, you actually said. And no, I didn't do anything wrong. As you can see from the picture, I'm decreasing, decreasing, decreasing. I level out at negative 4, and then I'm decreasing, and I'm decreasing some more. So what's my critical point? I don't have one. I mean, it's still a critical point, but that's not going to factor into my relative maximum or relative minimum. And here, I don't care about relative maximum or relative minimum because I care about absolute maximum and absolute minimum. And you might be thinking, well, then what do we do? Well, we still have to plug in these endpoints into the original equation to come up with our possible maximum or minimum. So if I take negative 6 and plug that in, that's going to be negative 6 plus 4. It's going to be negative 2. Cube that is going to be negative 8. And then negative that is going to be positive 8. If I plug in my other endpoint, negative 3, negative 3 plus 4 is 1. 1 cubed is 1. Make it negative. And so that right there is a max. That right there is a min. So my absolute maximum is going to be the point negative 6, 8. And that's my absolute maximum. My absolute minimum is going to be the point negative 3, negative 1. And you can see that from my picture. Here's negative 6. It's also way up here, so that's obviously going to be 8. Here's negative 3. It's way down there. It's obviously going to be negative 1. I mean, according to my picture, it's not perfect, but it serves its purpose. And negative 4 gives me nothing because what it does, again, is it goes down, levels out barely, and then goes back down again. So I have no max and I have no min there. No graph. Don't need it. That'll be my U. That'll be my V. We're doing product rule here. So U prime is going to be 1. V prime is also going to be 1. So the derivative y prime is going to equal U prime V, which is 1 times x minus 6 plus V prime U, which is 1 times x plus 4. Set it equal to 0. Those parentheses don't matter anymore, so combine like terms. x and x make 2x. Negative 6 and positive 4 make negative 2. Add 2. Divide by 2. And I have one critical point at 1. That's my CP. CP3PO. So I make a sign chart. 1 is my critical point. Let's plug in something smaller than that. Let's plug in something bigger. If I plug in something smaller to that into the derivative, I would get a negative because it would be 2 times 0 minus 2 is negative. If I plugged in 10, I'd get 20 minus 2, which is 18, which is positive. So whatever this is going to be some type of minimum. But if I'm doing absolute extrema, I also have to include negative 5 and 7. So I have to find y, the original y of 1, y of negative 5, and y of 7. So I'll just plug it into the original problem. If I plugged in 1, that would be 5 times negative 5, which is negative 25. That would be negative 1 times negative 11, which is 11. And that would be 11 times 1, which is also 11. Gasp! So this is my absolute minimum. And who would have thunk it? I have 2 absolute maximums. So abs max is going to be negative 5, 11, and 7, 11. How convenient. And my absolute minimum is going to be, what was it? 1, negative 25. Wow. Wow. Sounds like a guy from the Vine. All right, so this one's a banger. Not only do we find critical points, we have to find when this guy's increasing or decreasing, which, we did in the last couple problems. We just never really wrote it out. And we have to classify the critical points as relative maximums, relative minimums, or neither. So we kind of already did this problem. I take it back. When I said this problem was a banger, I thought maybe we'd have to deal with concave up and concave down. But I'm sure that's for later in the lesson. So I'm going to first take the derivative. Right, so what is that? 6x squared minus 18x minus 60. Right? Set it equal to 0. Probably factor out a 6. Leaves me with that. That's a 3. What do we got? 2 and 5 and 2. X minus 5, x plus 2. So my critical points are going to be set that equal to 0, nothing. Set that equal to 0, add 5, x is 5. And set that one equal to 0, subtract 2, negative 2. So those are my critical points. Okay, check. Now to determine the intervals for which the function is increasing or decreasing, what we're going to do is we're going to make ourselves a sine graph. So we have f prime here. Okay, I'm worried about negative 2. I'm worried about 5. So something to plug in smaller than negative 2. How about negative 10? In between negative 2 and 5, how about 0? And greater than 5, how about 10? And I'm plugging that into the derivative, which is this guy. So if I plug in negative 10, I'm going to get a negative times a negative, which is a positive. So that's increasing there. If I plug in 0, I'm going to get a negative. And if I plug in regular 10, I'm going to get a positive times a positive times a positive, which is a positive. So it's telling me to identify the critical points. I did. Now classify them as relative maximums or relative minimums. When my critical point is the change between an increasing to a decreasing, that means -2 is a relative maximum. And we can kind of see that by the way I draw this out. I don't write out the words, I write out the symbols. So what this means is whatever this guy is doing, it's increasing, and then at -2 it stops and then starts decreasing, which means it's the top of a hill. Similarly, 5 is going from decreasing to increasing. So 5 is a relative min. And what I forgot to do is say when it's increasing and when it's decreasing. So let me write that again. So I've got increasing, I've got decreasing. It increases from -infinity up to -2. So we will say x is less than -2 is when it's increasing. It's decreasing in between -2 and 5. So we'll say -2 is less than x, which is less than 5. And it also increases from 5 on. So we'll say x is greater than 5. We don't include the 2 or the -2 and the 5 because it's doing neither at those points. It's 0. Not bad. Not bad at all. Same problem. Oh, that's kind of boring. That's kind of boring. Y prime is going to equal 6x squared minus 20x plus 12. I can bring out a 2. Let me bring out a 2. That leaves me with 3x minus 10x plus 6. So I've got 2. Oh, you know what? Squared. Let me see. That probably needs to connect to a 6. Since that's negative and the 6 is positive, I have to have a double negative here. So your x minus and your regular x and your regular 1. Will that work? 3x squared minus... Nope. Let's switch the 1 and the 6. Oh, shoot. Which was which? 1, 6. So I've got that won't work either. Bummer. Do I have to do 2 and 3? Do I? Let's just do, I'm having a hard time here. I'm not sure why I'm struggling so much with this one. This might be a quadratic formula one. Because I'm not finding it. X minus 10. All right, let's do quadratic formula. I like having a good time. X equals -b, which is positive 10, plus or minus the square root of b squared, which is -10 squared, which is 100, minus 4 times a, which is 3, times c. So 4 times 3 times c is 72, all over 2a, which is 6. Making sure 4 times A times C is going to be 4 times 18. 4 times 3 times 6. Oh, do I not have you on? Yeah, it was 72. All right, so this becomes, that's why I couldn't factor out. You can't. The square root of 28 over 6. It's not factorable. So I'm going to have 2 terrible critical points. Terrible critical points. 10 plus the square root of 28 divided by 6. That won't do it. 10 plus the square root of 28.
The answer is approximately 15.2915.
15.2915 divided by 6.
It's about 2.5485.
What did I do? Minus 10 minus the square root of 28. 10 minus the square root of 28.
The answer is approximately 4.7085.
4.7085 divided by 6.
The answer is about 0.7847.
Barf. So let's make ourselves a sine table. So I have 0.7847 and I have 2.5485. I can plug in 0. I can plug in 1. And I can plug in 10. So if I plug in 0 into the derivative, I get a positive. If I plug 1 into the derivative, I get 3 times 1 minus 10 plus 6.
The answer is negative 1.
Negative. And if I plug in 10, 3 times 100 minus 100 plus 6.
It's 206.
All right. So things kind of acted nicely. So my increase happens all the way up until 0.7847 and then starts up again after 2.5485. And we can see that that's the case here, and that's the case here. It decreases in between those two numbers. So 0.7847 is less than x, which is less than 2.5485. Not fun. Not fun at all. Since I'm going from increasing to decreasing, 0.7847 is a relative max. And then 2.5485 is a relative min. Oh, why couldn't you just factor u? There's our inflection points. There's our concave up and concave down. It took a while. Well, in order to get concave up and concave down, you do the same thing, but you find the second derivative. So derivative number 1 is going to be 0 plus, let me make that an equal sign. 0 plus 12x minus 3x squared. Derivative number 2 is going to be 12 minus 6x. set it equal to 0. Subtract 12. Divide by -6. And your one and only inflection point is going to be 2. Or possible inflection point. So we make a sine graph for the double, the second derivative. Magic happens at 2. So I'll plug in 0, I'll plug in 10. And I'm plugging it into the second derivative to find when it's concave up and concave down. Inflection points are like critical points for the second derivative. Concave up and concave down is like increasing and decreasing, but for the second derivative. So if I plug in 0 into the second derivative, I'm going to get a positive, which means concave up. And if I plug in 2, I'm going to get 12 minus 60, which is going to be negative, so concave down. So we could say concave up for everything up to 2. So x is less than 2 is concave up. And concave down, concave west, Kanye. Concave down is everything after 2. And at 2, we have a change in concavity, which is what happens every time I go to the dentist. Because he gives me a cavity. Well, I have a cavity, but he gives me a filling, and there's no longer a cavity there. That was easy. Too easy, in fact. I don't know why anyone's still watching this if you still are. Barf! Although, after taking the second derivative, I should bump it down to a quadratic. So maybe not so barf. I don't know. We'll see. Same exact directions. The first derivative is going to be 4z cubed minus 36z squared plus 84 plus 0. Second derivative is 12z squared minus 72z plus 0. Set it equal to 0. Bring out a 12 and a z. And that leaves me with the z minus 6. Set that one equal to 0, the first one, the 12z, set it equal to 0, divide by 12, and you do get an inflection point of 0, or a possible inflection point. Set that equal to 0, add 6, and you get 6. Let's make a sine graph for g double prime. Possible inflection points are 0, and 6. So I can plug in -10. I can plug in 5. And I can plug in 10. And I'm plugging that into the second derivative, which is this guy. So let's do it. 12 times -10 squared minus 72 times -10.
The answer is 1920.
Hey, Mr. Perich, isn't that the year you were born? Ha 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 ha! No. It was not. 12 times 5 squared minus 72 times 5.
The answer is -60.
12 times 10 squared minus 72 times 10.
The answer is 480.
So those are my inflection points, legit. So we are concave up for everything less than 0 and everything greater than 6. And we are concave down for everything in between 0 and 6. Usually the critical points and inflection points are all thrown into the same problem, and every now and then you'll be asked to sketch what a possible graph would look like. I don't know if I built that into this crash course. Oh, Lord, please, I pray that I didn't, because those are not fun at all. Oh, yeah, the good old optimization problems. Usually with optimization problems, usually not always, you will be asked to maximize or minimize something. And usually it requires two equations that you have to combine into one. So we have two positive numbers whose sum is 300. So x is a positive number, y is a positive number, the sum is 300. Okay. What else? You have to maximize the product. So the product, I'll just make it capital P, is going to equal x times y. Well, my job is to maximize the product. So my goal is to maximize this. The issue with maximizing that is I have an x and a y. But since I already created that equation, all it would take me is for me to subtract x from both sides, and then y becomes 300 minus y, x, 300 minus x, pardon me. And now I could take what that y is and plug it into that equation right there. So I am to maximize my product, which is x times 300 minus x, aka, also known as 300x minus x squared. The way I maximize it is I first have to find the critical points. So set that equal to 0 and take the derivative. So I now have 300 minus 2x. If I subtract 300 and divide by -2, then my critical point is going to be 15. 150, I mean. Again, I've been at this for like an hour and a half, I feel. Critical point is 150. Good. What I also have to consider is the largest possible number that I can use and the smallest possible number I can use. Okay, so my critical point is what I'm going to end up plugging in to the original maximize equation, which is this guy, to see if it'll give me the maximum. Okay, also, I have to consider what we call our endpoints. Every now and then, we know that the endpoint could also possibly be our answers too. So the largest possible number that I can use for this is 299.9999999. So one endpoint is 300. And the smallest possible number that I could use is 0.0000001. So I'll just call that 0. And maybe what I should do is I should make that a rounded. So I'm not necessarily including it, but it's so close. And we already know from limits that, it's going to be close enough. So what I'm going to do is I'm going to take my critical point. I'm going to take my two endpoints and plug that into the original maximizing function to see which gives me the maximum. The two positive numbers whose sum is 300 and whose product is a maximum. So if I tried P of 0, P of 300, those are my endpoints, and P of 150, that is my critical point. If I plug 0 into this equation right here, I would get 0 times who cares, which equals 0. Okay, so my sum would be 300, but my product would be 0 because I'm saying, let's just take 300 and multiply it by 0.0000000. And at that stage, we're like, that's like nothing. If I tried 300, I would get 300 times 300 minus 300, which is 0. So the whole thing becomes 0. So that's useless. If I try 150, that would give me 300 times 150. So this is 150 squared, 150 squared.
I found this on the
150 squared.
150 raised to the second power is 22,500.
And so the numbers that would do that are 150 and 150. So if we found out that x is 150 and the x being 150 is what makes that work, then the other number is going to come from the y. The other number is going to come from 300 minus x, which is also 150. Which, if my hopes and dreams are coming true, is going to nicely bleed into the next problem. And I was wrong. Although, let's do this one first, and then we'll go back to the barn problems. So this is going to bleed very nicely into the fenced-in area problems, okay, which follows the same exact rules. I have a fence that's a rectangular fence. So I'm given 800 feet of fencing. So I have a rectangular fence. Let's call you X. Let's call you Y. Okay. I am given 80 feet of fencing. So the perimeter of a rectangle is 2 times the length plus 2 times the width. It is equal to the perimeter. So my perimeter is 80. And that's going to equal 2 X's plus 2 Y's. My job is to maximize the area, and the area is found by multiplying the length and the width. So I have to maximize this guy. Well, I can't because there's 2 letters there. If I just solved this guy for y by subtracting 2x from both sides and dividing everything by 2, I get 40 minus x equals y, which I can now nicely plug into that. So the area that I'm going to maximize is going to be x times 40 minus x, or I'm going to maximize 40x minus x squared. And if you're looking at this and saying, boy, oh boy, that sure looks a whole lot like the last problem. Yeah, it should. It should. It should. The derivative is going to give us a critical point. The derivative is 40 minus 2x. Set that equal to 0. Subtract 40, negative 40. Divide by negative 2, 20. And my one and only critical point is going to be 20. So this guy, muy importante. This guy, muy importante. The other thing that's very important are the endpoints. The smallest possible side that I can have here is 0. I can build a fence where I make one of the rectangular sides 0.00001 feet if I wanted to. So I could have a size of basically 0. And again, why don't I make this a closed one, or an open one, so 0. And the largest possible side that I can have is 40. Why not 80? Because if I have to make a rectangular fence and this side is 40, then the opposite side has to be 42. And the sides connecting them are basically going to be nothing. So I have endpoints of 0 and 40 and a critical point of 20. So what I have to do is I have to plug it into the original. So I guess, yeah, I have to plug it into the original function to see what side gives me the maximum. So a of 0, a of 40, a of 20. All right, so if I plug 0 into this guy right here, the one that I said was muy importante, I'm going to have 0 times, who cares, it's going to be 0. If I plug in 40 into this guy, it's going to be 40 times 40 minus 40, which is 0, so the whole thing becomes 0. If I plug in 20, I'm going to get 20 times 40 minus 20, which is 20, so 400. Which means x equals 20 is my maximum x. How do I find my y? By going over here and saying 40 minus 20 is my y. So my side measurements that are going to maximize my area are going to be 20 feet by 20 feet. So if basically all you're doing is trying to maximize something, and you have all parts that you have, it's always like if you're maximizing a rectangular fenced-in area, it's always going to be a square if you have all 4 sides of the rectangle. Always going to be a square when you have all 4 sides of the rectangle, and this is closely related to the last problem that we did. Now, I said twice, if you have 4 sides of the rectangle. Well, what if you don't? So now you have a barn. There it is. B for barn. And you have a rectangular fence where you're using the 4th side, and the barn is the 4th side. We'll call you X, we'll call you X, we'll call you Y. So what you have to be careful of is the 1,200 feet of fencing that you have is going to be built from 2 sides of this X length and 1 Y. So it's 2X plus a Y is going to equal the 1,200 foot of fencing. My job is to maximize the area, which is still going to be X times Y. Now, I have to maximize that, but I can't because there's 2 letters. But if I just subtract 2x from this guy, then I'll have 1,200 minus 2x. So then I can say A equals x times 1,200 minus 2x, which A then is going to be at 1,200x minus 4x. I wanted to make this smaller. Is this the button? No. All right. Well, can I do that? Can I pinch? No. We'll move you here for now. All right. So I need to take the derivative. So the maximum area problem, very important. Take the derivative, set it equal to 0. So I have 0 equals 1,200. Well, I have to take the derivative, so it's just going to be 1,200. This was supposed to be squared. My bad. So that shouldn't be 4x. I think I accidentally took the derivative without thinking. All right. Got to finish this problem quickly. My computer's telling me I'm running out of space. So this was supposed to be 2x squared. My fault. So the derivative of that would be minus 4x. Add 4x to both sides, divide by 4, and you would get x equals 300. So that's my critical point. What's the largest y value I can have? What's my end point? The largest y value I can have is 1200. Although I don't care about y, I care about x. So the largest x value I could have is 600. The smallest I can have is 0. So I'm going to plug my critical point, 0, and 600 into this equation right here, which I said was very important, or that equation. So I'm going to do a of 0, a of 600, and a of 300. Just because I'm running out of space on my computer, I'm telling you right now, a of 0 is 0, a of 600 is also 0, a of 300 is going to be, I think it's 300 times 600. So that would do it. So the x value of 300 is what gives me my maximum value. The y is going to be 1200 minus 2 times 300, which is 600. So it's going to be 300 feet by 600 feet, which is different from the last one. The last one was a perfect square. This one's not. Interesting. Very interesting. Very interesting. Somebody call the wambulance because we're going to talk about L'Hospital's rule. It's actually pronounced L'Hopital. He's French. And what L'Hopital, by the way, I am in a classroom of 5 young people who are going to ruthlessly make fun of me the entire time I do this. Can't wait. All right, so what L'Hopital's rule says is if you take a limit, and after taking the limit, you get 0 over 0, like that guy. Oh, I have to press this thing. Yeah, I have a new thing. I have a new toy that I'm borrowing from a friend. Will that work? Yeah. If you get 0 over 0, like that guy, or if you get infinity over infinity, like that guy, L'Hopital's rule says just take the derivative of the top, take the derivative of the bottom, and try it again. So if I were to plug in infinity, right, I would get ln of 3 times infinity, which is infinity. So the whole thing would become infinity. Infinity squared is infinity. And that is a problem according to this guy right here. So what I do is I take the derivative of the top. So I would have the limit. Wow, I have to get used to this thing. As t approaches infinity of, let me see, ln of 3t's derivative is 3 over 3t all over 2t. So I can cross those 3 over 3t's out. Remember, there's a rule that says if I plug in infinity to a denominator, it turns the top into 0, the whole thing into 0. So that's supposed to be a 0. That's going to become infinity. 0 over infinity is 0. So 0 over 0 is bad. Infinity over infinity is bad. 0 over infinity is not bad. Or as Eminem would say, not so bad at all. So I have sine of pi w. Do I have my phone? I do. I have sine of pi w over w squared minus 16. So let's just double check. Sine of negative 4 pi.
One sec.
Take your time, buddy.
The answer is approximately 2.37757.
Sine of negative 4 times pi.
The answer is approximately 2.37757.
It's not at all giving me what I want. Actually, it should be just sine of pi.
I didn't get that.
Sine of pi. 0, isn't it?
I found this on the web.
It is. Yeah. So that'll become 0. Negative 4 squared is 16 minus 16. That'll become 0 too. All right, so let's take the derivative of the top. So that's chain rule. So bring the pi out. Cos pi w over 2w. So let me see what I get on the top when I plug in negative 4 now. It'll be cos pi.
The answer is negative 1.
Okay, so this will be negative pi on the top because pi times negative 1 over negative 8. So let's cancel out the negatives and I get pi over 8. I ate pi, but pi over 8, that's different.
Can he come read to me over here? Because he's going to read out loud that every.
I'm not editing anything. These kids wanted me to make a video for them. It's going to be 4 hours long. I'm not editing anything. Whatever happens, happens. If I plug in 2 up here, that'll be 2 cubed minus 7 times 4 plus 10 times 2.
The answer is 0.
2 squared plus 2 minus 6.
The answer is 0.
So I'm going to take the derivative. So I have the limit as x approaches 2. That's supposed to be an arrow. X approaches 2. The derivative is going to be 3x squared minus 14x plus 10 over 2x plus 1. And this should work out just fine. 3 times 2 squared minus 14 times 2 plus 10.
The answer is negative 6.
Mm-hmm. And then this is over 5. There you have it. There you have it, ladies and jelly spoons. Ladies and germs. L'Hopital. So much fun I can barely contain myself. All right, we talked a little bit about rectilinear motion, just a teensy bit, just a smidge. When we did stuff at the beginning of the video, and we said that taking the derivative gets you a rate, and the most common rate that we will deal with is velocity. Well, rectilinear motion is basically, I'm going to give you this equation right here, and this equation represents basically what a roller coaster looks like, and at time t, whatever t is, whatever t is the time, and wherever t is going to be where my roller coaster car is. So S is going to give me the position of we usually call it particle or an object or the roller coaster car. The velocity function is found by taking the derivative. So S prime of t, I'm going to call v of t, and in this case, that's going to be 2t minus 12. I'd rather be sipping tea than 2t. Am I right, kids? Tea is gossip. And so anyway, the second derivative is going to give me the acceleration. So I'll call that a of t. And that's just regular old 2 no matter what. Easy. So did I find the velocity and acceleration functions? Yup. Now I need to find the velocity speed, and acceleration at the 5th second. So let's plug some stuff in. The velocity is going to be me taking 5 and plugging it into that t right there. So v of 5 is going to be 2 times 5 minus 12, which is negative 2. Do I have units? No, I don't. So it would be like feet per second or miles per hour, whatever. Now, speed is going to be the absolute value of your velocity. So since the velocity was negative 2, speed is going to be the absolute value of negative 2, which is positive 2. When the velocity is negative 2, that means I'm going downward at 2 miles an hour or backwards at 2 miles an hour or whatever it is. If I'm going backwards 2 miles an hour, then my speed is 2 miles an hour. So we're just going to word it out like that. My acceleration at 5 is going to have me plugging 5 into 2, which is just 2. And usually that would be given to us as meters per second or meters per second squared or feet per second or miles per hour. A particle is traveling along the path. Is it the same exact problem? It is. I just made a second part 2. A particle is traveling along the path of the equation right there. When is the particle stopped? The particle stopped when the velocity is 0. So again, the velocity function is the derivative, which we found to be 2t minus 12. The particle is stopped when the velocity is 0. So 0 equals 2t minus 12. Add 12 to both sides. Divide 2. And it is stopped at 6 units. Probably seconds, minutes. Doesn't really matter. One thing you have to be very careful of is if we do a problem and it's like a quadratic and you have 2 answers and maybe you have like 6 units and negative 3, there's no such thing as negative time. Okay? So for any reason, if we do a problem like this and there's several answers and one of those answers is negative, get rid of the negative answers. You can't have negative answers. It's impossible. This guy is, when is it speeding up or slowing down? It's speeding up or slowing down when the acceleration is positive, speeding up, or the acceleration is negative, slowing down. The acceleration, no matter what, is 2. Now, normally what I would do here is I would find my inflection points. That's supposed to be a straight line. I'd find inflection points. I would do a S double prime thing, and whatever's going upward is going to be speeding up, and whatever's going downward is going to be slowing down. But since no matter what, it's going to be positive, it's always speeding up. Like when I drive my really expensive flashy car down the highway. My Honda Civic. Just kidding, I have a Nissan Pathfinder. That's it for rectilinear motion. So the 2 main important things in calculus are derivative and integration. Simply put, integration is the opposite of a derivative. It's the antiderivative. And just like with everything else, there's a set of rules that we have to follow. So we have the integral of x to the n dx is 1 over n plus 1, x to the n plus 1. So simply put, if I have x to the, I keep doing that. If I have x to the third, you make that 1 over 3 plus 1, x to the 3 plus 1, and then simplify that into a third or a fourth, x to the fourth. Remember that every now and then, 1 over x can be written to you as x to the negative 1. So the integral of x to the negative 1, or 1 over x, is going to be ln absolute value of x. The integral of cosine is sine. The integral of sine is negative cosine, the opposite of the derivative. Don't worry about this guy right here. Just worry about the integral of secant squared x is tangent x. And if you're like, those plus c's, what are those? What are those? It's still funny after all these years. We'll talk about that in a little bit. But the integral of e to the x is e to the x. No surprise there. Okay, definite integrals are going to be integrals that have no numbers attached, and you just take the integral and you always attach a plus c because that could mean some arbitrary constant that we don't know. So showing all my steps and taking all of my time, I have a 10 living outside. I'm going to make that 1 over negative 3 plus 1 t to the negative 3 plus 1. And I'll clean that up in a minute. Plus, let's have the 12 out here. So 1 over negative 9 plus 1 t to the negative 9 plus 1. I'll clean that up in a minute. Plus, bring the 4 out, 1 over 3 plus 1, t to the 3 plus 1. And then with the definite integrals, it's always going to be plus c. That's supposed to be a c. Now it's a c. Or as our Spanish friends would say, yes. Okay. So I have 10 times 1 over negative 2. So that's negative half of 10, so negative 5. T to the negative 3 plus 1 is negative 2. Pretty simple. 12 times 1 over negative 8, which is minus 3 over 2. T to the negative 8. And then we've got 4 times a fourth. Oh, that's easy. 1. T to the fourth plus c. Overachievers be like this. Let's move that t to the negative 2 to the bottom. That's where Drake started. Let's move that t to the negative 8 to the bottom. That's where Drake started. And then plus t to the fourth. And then plus c. All right, so we've got 4 times, that's a 6. So 1 over 6 plus 1 is 7. X to the 7 minus 2. 3 plus 1 is 4, so 1 over 4 x to the 4 plus 7. That's an invisible 1. So 1 over 1 is 2, x squared. And if it's just a constant, you just attach the x. Plus c. 4/7 x to the 7th minus a half x to the 4th plus 7 over 2 x squared minus 4x plus c. Fun. You know what they say, you can't spell functions without fun. Am I right? Mm-hmm. Or as the kids say, sheesh. So good to be back. All right. Let's blow that up a little bit. Let me rewrite that guy out, move my face, and rewrite that guy out to this. Integral of 4x to the negative 2 plus 2 minus 1/8 x to the negative 3. That's a negative 3. Let me make it look better. Dx. So we've got 4. Negative 2 plus 1 is negative 1. So 1 over negative 1, x to the negative 1. Plus 2, attach an x. Just attach the x. Minus 1/8. Up. I have x to the negative 3, so I need to put 1 over negative 3 plus 1, which is 1 over negative 2. X to the negative 3 plus 1 is negative 2. And the plus c right there, all small. So 1 over negative 1 is negative 1 times 4 is negative 4. Negative 4. And I'll just put that right over x because I can. Plus 2x. Let me see. Negative 1 over 8 times negative 1 over 2 is positive 1 over 16. And then let's move that x to the bottom where Drake started. What's that? So I'm going to rewrite this out. Integral of 6w to the negative 3 minus 2w to the negative 1. Be careful. dw. So this is going to become 6 times 1 over negative 3 plus 1 is negative 2. W to the negative 3 plus 1, which is negative 2, minus 2 ln of w. Gotcha. Got to be careful. Got to be careful with those w to the negative 1s. They'll get you every time. So we'll clean it up. Negative 3, and I'll put it over w squared because that negative 2 brings it to the bottom. Minus 2, where Drake started, minus 2 ln of w plus c. Not even going to ask. Okay. Super easy, almost too easy. Integral of sine is negative cosine. Oh, an angel just got his wings. Let me turn that angel off. Negative cosine x plus 10 tangent x. Oh, it's actually cosecant squared. Oh. Integral of cosecant x squared. Squared x. That would actually be cotangent. No. What's the integral of it's secant squared x is tangent. The integral of cosecant squared then would be cotangent? I feel like that's too easy. I feel like that's not right. Integral of cosecant squared x. Negative cotangent x? Thanks. So we'll turn that into just what was said. Negative cotangent squared or negative cotangent?
Just negative cotangent.
Okay. So we have that. plus c plus c. That wasn't me. All right, so here we are at integration by substitution. The list of rules that you saw a few slides ago, the integral of sine x, the integral of e to the x, those are just straightforward integration problems. However, when you look at chain rule looking type problems within an integral, that's when you're going to use what's called U substitution. What you're doing is you're going to find a function that looks like it has a derivative or close to a derivative floating somewhere else in the integral. And you're going to call that U. Usually, not always, but more often than not, the stuff that would be inside of a function is normally going to be our U when we have chain rule looking things. And this is no different in this problem right here. I'm going to allow this guy to be U. And I'm going to let that be U because it looks like its derivative, which is going to be something x squared, is floating around here. So I'm going to say, let's let U equal 2 plus 6x to the third. I'm going to take its derivative. So the derivative of a U is du dx. So du dx is going to equal 18x squared. I'm going to flip the 18x squared and the dx. So I'm going to treat it like, what's it called? Like it's 2 ratio. It starts with a p, a proportional. I'm going to treat it like that and just do like a flipperoo with the dx and the 18x squared and flip. So I'm going to have du over 18x squared equals dx. Now what I'm going to do with that is I'm going to rewrite the original integral but substitute two things. Instead of 2 plus 6x cubed, I'm going to turn that guy into a u. And instead of dx, I'm going to replace it with du over 18x squared. So let me write that out. The integral of 90x squared sine u, and instead of dx, I have du over 18x squared. Now, if I do this right, and usually you do, you should see all the x values cross out. So I have an x squared up here and an x squared down there. They cross out. What also not crosses out but simplifies is I have a 90 up here and an 18 down there, which is going to simplify into a 5, which I'll bring out front. Now, by doing this, I have 5 times the integral of sine u du. Now, that is an integral that I can take based off of the 6 or 7, however many basic integrals that I showed you a few slides ago. So the integral of sine u is negative cos u. So I have negative 5 cos u plus c. And since I didn't have any u in the original function, I have to make sure I substitute the u that I created back into the answer. So I have negative 5 cos parentheses 2 plus 6x cubed plus c. That's integration by substitution. Pretty involved. Lots of steps. Lots of steps. All right, so let's do it again. Let me zoom up. There we are. All right, so I have to choose a u. And the u that I choose is going to have a function that appears like its derivative is floating somewhere else in the integral. So I really have two options, 8x minus 12 or 4x squared minus 12x. Now, if I took the derivative of this guy, it would be just 8. Well, I don't have a just 8 floating around. If I took the derivative of this guy, I would get 8x minus 12. Oh, how about that? It also shows that this guy right here is living inside of a parentheses with a 4 attached. So once again, what appears to be a chain rule looking type problem, that's going to be where I pull my u from. So u is going to be 4x squared minus 12x. So I'm going to take the derivative of that u with respect to x. So du, whoopsies, bumped the screen. Du dx equals 8x minus 12. All right, so now this is the part where I do the old flipperoo. I'm going to swap the dx into 8x minus 12. So I'm going to have du over 8x minus 12, and that's going to equal dx. So I'm going to take that. I'm going to rewrite the original integral, and I'm going to substitute two things. I'm going to replace this guy with u, and I'm going to replace that guy with du over 8x minus 12. So I have the integral of 8x minus 12 times u to the fourth. And instead of dx, I have du over 8x minus 12. Now, the 8x minus 12 on the bottom is a group, and I have an 8x minus 12 on the top there, so I'll cross both of them out. Perfect. I'll rewrite it out. So I have the integral of u to the fourth, which is something I could easily handle, du. So I'm going to integrate with respect to u. So the integral of u to the fourth is 1/5 u to the fifth plus c. My last step, however, is to replace the u with what I had in the first place, which is 4x squared minus 12x. So my final answer is going to be 1/5 parentheses 4x squared minus 12x to the fifth plus c. And that's it. Much easier than war. I think. I've never been. Never been. All right, take the integral again. So I have what appears to be, it appears like it's quotient rule. Many times when we have the integral of a fraction, I look to see if anything will disappear, and I'm not seeing anything that could possibly disappear, at least not right now. Nothing seems to simplify. No, you can't cross out 4w. No, you can't cross anything out because we're adding and subtracting on the top and the bottom. Looks like I'm going to have to use integration by substitution. So my u is going to be, and again, and it seems like the trend here, because in the last two problems, it looked like the stuff on the inside was going to be our u. Well, I don't have stuff on the inside, so I'm going to have to rely on what looks like something that has the derivative somewhere else. Well, this is a quadratic because its degree is 2, and this is linear because its degree is 1. So taking the derivative of a quadratic would give me something linear, so I'm going to allow the denominator to be my u. So u is going to equal, let me blow this up. I like blowing it up a little bit. Oh, can I just get rid of that u? Nope. Thought I could. Thought I could. All right. Let's let u equal 4w squared plus 6w minus 1. The derivative of that u, du dx, is going to be, want to change colors, du dx is going to be 8w plus 6. Flip. So du over 8w plus 6 is going to be my dw, which I think was the name of a character from a TV show with a mouse or something like that. Why is that that random useless trivia just popping in my head. All right, so let's rewrite the original guy, replacing a few things. So 4w plus 3 doesn't seem to change over u. And I have du over 8w plus 6. Now here's the thing. I'm not allowed to just go because they're not the same. But you know what? It looks like this denominator, if I were to factor out a 2, that would leave me, let me see, 4w plus 3 over u. That's supposed to be a 3, and it looks like the letter B. Du, factor out a 2, and I would get, oh, no way. No, who didn't? I would have never guessed. So cross u out, cross u out. I'll bring the 2 on the bottom out in front and make it a half. And the integral is going to be 1 over u du. The integral of 1 over u is ln of x. So this becomes 1/2 ln of u plus c. What was u? That guy right there in black. That guy right there in black. Galaxy Defenders. It's been a long day. Ln of 4w squared plus 6w minus 1 close absolute plus c. Boom. I can barely contain myself. This, ladies and gentlemen, boys and girls, is a definite integral. The difference between this one and the last one is this has something called limits of integration. Remember, when you take the integral, you're finding area. Now, we actually, and it's going to be area underneath the curve. Now what we do is we have to say start here, stop here, and we're actually going to find an actual number. No more plus c's. So when we don't have the numbers, you always attach a plus c. The difference with this one is, and let me pick a nice color that's a little bit bright so you can see in the blue. This is what's called my upper limit. This is what's called my lower limit. Okay? And so we'll say f of x dx. What you do is you take the integral, plug in b, take the integral, plug in a, and then subtract the antiderivative of the one with b minus the antiderivative of the one with a. No more c's. So we'll get a number here. I don't know if the number is going to be nice. Looking at it, probably not, but we'll get a number here. All right, so the integral, upper limit 4, lower limit 1, 8. And I'm going to write this as t to the negative 1/2. I did two things here. I brought the t up top and made it, well, first off, I took this t on the bottom and I made it to the half, because it's square root. Then brought it up and made it t to the negative 1/2. Minus, and I'm going to call this 12 t to the 3 over 2 dt. Okay. So that becomes 8 times 1 over 1 plus negative 1/2, so 1 minus 1/2 t to the 1 plus negative 1/2, which is 1 minus 1/2. Gross. Minus 12. 1 over 3/2 plus 1, so 1 plus 3/2 t, 1 plus 3/2. Now, usually at the end of these problems, you put a nice big line and you remind yourselves that you have limits of integration. Okay? So there that is, the limits of integration. Oof. I did not do a good job giving myself space at all. All right, let me move my face. Hello, problem. All right, so we have, let's do a little bit of math in our heads. 1 over 1 minus a half is a half, so that's going to become 1 divided by a half is 2. So this becomes 16 square root of t, because this becomes 1 minus a half, which is a half, and so t to the 1/2 is square root of t, minus, this is going to become 1 over 1 plus 5 halves, 3 halves, which is 5 halves. Flip that upside down, which is 2/5, and this becomes minus 24, actually, over 5. And then that becomes oh, did I write out the wrong thing? I did. That should have been 3 halves. So that becomes 5 halves. T to the 5 halves is the square root of t to the 5th. Very unpleasant. All right, so watch me zoom. My limits of integration were 4 and 1. So now I'm going to do that. I'm going to have 16 times the square root of 4 minus 24 fifths times the square root of 4 to the 5th minus 16 times the square root of 1 minus 24 fifths times the square root of 1 to the 5th. I can handle that one. That becomes 32. The square root of 4 to the 5th is 32. So it's going to be minus 24 fifths times 32 minus 16 minus 24 fifths. All right, let's see if we can break this down nicely. 32 minus 24 fifths times 32. So I got negative 121.6. 16 minus 24 fifths.
It's 11.2.
Negative 121.6 minus 11.2.
It's negative 132.8.
At least we were given 4 and 1. Otherwise, it would be a terrible, 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 terrible answer. Terrible. Or as Charles Barkley would say, terrible. My favorite athlete of all time. Okay. All right, let me zoom up. So straightforward, no manipulation necessary. This is going to be 12. This is going to be 12 times 1/4 x to the 4th, close it, minus 9 times 1/3 x cubed, close it, plus 2x. Limits are 6 and 1. So 3x to the 4th minus 3x cubed plus 2x, limits of 6 and 1. So we'll do the limit of 6 in what is this color? Blue. So I have 3 times 6 to the 4th minus 3 times 6 cubed plus 2 times 6, close it, minus, we'll do this in green, 3 times 1 to the 4th minus 3 times 1 cubed plus 2 times 1, close it. Three times 6 to the 4th minus 3 times 6 cubed plus 2 times 6.
The answer is negative 617.25.
That can't be right. What did I... Oh, I thought I said times 1/4. 3 times 6 to the 4th minus 3 times 6 cubed plus 2 times 6.
The answer is 3,252.
3 times 1 minus 3 times 1 plus 2.
That would be 2.
And I can handle this mental math. $3,250. Much nicer. So when you graph this, okay, this is going to give you some cubic function. I don't know what it looks like. So I'm just going to make up a cubic function right now. Okay, that's what a standard cubic is going to look like. Between 1 and 6, this is going to be the area underneath. So 320 or 3,250 square units. Cool. Pretty tough. Huh. Pretty hard. All right, so we've got ourselves a nice little trig problem. I think I can handle it. All right, so let me see. The derivative, the integral of sine is, I keep doing that. The integral of sine is negative cosine. So negative 7 cos t minus 2, the integral of sine is, of cosine is regular sine, so minus 2 sine t. Limits are pi over 2 and 0. Nothing crazy yet. So I've got negative 7 cos pi over 2 minus 2 sine pi over 2, close it, minus negative 7 cos 0 minus 2 sine 0. Cosine pi over 2.
The answer is negative 1/2.
Cosine of half a pi.
Here's what I found.
Cosine of pi divided by 2.
The answer is negative 1/2.
Yeah, it's not giving me the answer I want. Let me consult the Wolfram Alpha. Cos pi over 2. I put po over 2. Oh. 0. So that becomes 0. Let me change this to sine of pi over 2. So that's 1. So minus 2 times 1 is minus 2. Minus cosine 0. That's 1.
1 sec. The answer is 1.
Yeah. Sine 0. 0.
The answer is 0.
Okay. So I have negative 2 minus negative 7, which is 5. What a nice, lovely number. Who would have thought? Now we're going to do integration by substitution, but we're using definite integrals. So the rules don't change. I need to find a u that looks like its derivative is floating around elsewhere. Also, I have an e to the stuff that's not x, or in this case, w. So I'm going to let u equal the 1, and let me do the zoom up thingy that I like to do. So zoom up, erase. All right, so I'm going to let u equal 1 minus, and I'm going to rewrite that as w to the 3 halves. So the derivative, du dw, is going to equal 0 minus, drop down the 3 halves and subtract 1 from 3 halves, and I get that. Do the old flipperoo. So du over negative 3 halves, and I'm going to change that to the square root of w so that it looks more pleasant when I decide to go. It's going to equal dw. So allow me to rewrite this as the integral upper limit 4, lower limit 1 of the square root of w e to the u, Eastern University, du over, I lost my train of thought, negative 3 halves square root of w. Cross u out. Cross u out. I'm going to bring the over 3 over 2 out front and do the reciprocal. So negative 2/3 integral between 1 and 4 of e to the u du is going to be this. Negative 2/3 e to the u, because the derivative or integral either way of e to the u is e to the u. But what I have to remember are my limits of integration, and my limits of integration are for the x values and not for the u values. So I'm going to write out x equals 4 and x equals 1 because my limits of integration are for x. So I have to remind myself to plug in what u originally was back into the original equation before I start plugging in my limits of integration. So I have negative 2/3 e to the 1 minus square root of w cubed, with my limits of integration being 4 and 1. So I have negative 2/3, I'm running out of room, negative 2/3 e to the 1 minus the cube root, or the square root of 4 cubed, minus 2/3 e to the 1 minus square root of 1 cubed. Square root of 4 cubed is 8.
The square root of 4 cubed is 8.
So what I have is I have 1 minus 8. So I get negative 2/3 e to the negative 7 minus negative 2/3. That should have been a negative, so plus 2/3. That becomes 1. 1 minus 1 is 0. E to the 0 is 1. And 2/3 times 1 is just 2/3. I probably, if I had more space, I would have made that negative 2 over 3 e to the 7th plus 2/3. But who's counting? I mean, we're like, what, 3 hours into this thing? 3 hours? I shot this video in 2 days. It's like 9 o'clock at night right now. Screaming kids all day long. Boy, oh boy. Take the integral. All right. I'm going to let this be my u because it has a degree of 5. And this has a degree of 4, so that would make sense here. Let me blow that up. So u is 10x squared plus x to the 5th minus 2. Du dx is going to be 20x plus 5x to the 4th. Flip du over. Now I know what's going to happen, so I'm just going to get this out of the way. I know that somehow that's going to cross out, but the only way I'm going to make that cross out is if I bring a 5 out of that guy right there. So I'm going to bring the 5 out now and make that 4x plus x to the 4th. At this stage, you should know what's coming. That's going to equal dx. So I'm going to rewrite the integral. The integral, lower limit 0, upper limit 1, 3 times 4x plus x to the 4th, cross u, or not cross u out, I'm getting ahead of myself, u to the 6 du over 5, 4x plus x to the 4th. Cross u out, cross u out. I'm going to bring a 3 out on top, 5 out on the bottom, 3 on top, 5 on the bottom, integral 0, 1, u to the 6th, du. That becomes 3/5 times the integral of u to the 6th is 1 over 7 u to the 7. Limits of integration are x is 1 and x is 0. 3/5 times a 7th is going to be 3 over 35. U was 10x squared plus x to the 5th minus 2. And my limits are 1 and 0. All right, I should be good for that. Okay, here we go. 3/35. 10. 1 squared plus 1 to the 5th minus 2. Close, close. Minus 3/35. 10. 0 squared plus 0 to the 5th minus 2. Close, close. So that's going to be 10 plus 1 minus 2 is 9. So 27 over 35. Minus 0 plus 0 minus 2. So minus negative 6. So plus 6 over 35. And that's going to give us 33 over 35. All right, so we're now given a velocity function, and we are being asked to kind of do the opposite of what we've done before. If I would have given you a position function and I wanted to find velocity, I'd take the derivative. Now I'm given the velocity function, and I'm talking about position. Now there's two different types of position here, displacement and distance. Okay, displacement is basically if I were to throw a ball as high as I could up in the air and it goes 50 feet up and then 50 feet down and lands 2 feet in front of me, that ball traveled 2 feet. Or technically, if I throw it up 50 feet and it comes down 50 feet and I catch it, it travels 0. That's displacement from the beginning to the end. However, the distance that I throw it is if it goes up 50 feet and it comes down 50 feet, it traveled 100 feet. That's the distance between the two. Displacement is just a regular old integral. Okay? Distance is an integral, but we have to take in effect what's called the absolute value. So I'm going to have to do some sign changes and stuff like that. It's not that much fun, but it's not that bad. So let's zoom up. I need distance and I need displacement. The first 5 seconds. So I'm going to do displacement first. So I'm going to take the integral, and it's the first 5 seconds, so between 0 and 5, of 2t plus 1 dt. So that's going to become t squared plus t limits of integration 0 and 5. I'm going to end up with 5 squared plus 5, 30, minus 0 squared plus 0, 0. And that's going to end up being 30 minus 0, which is 30. Feet, what was it? 5 seconds. Meters. Meters per second the first 5 seconds. So the displacement is meters. So the way we find distance, we have to consider the fact that the displacement is I'm 30 meters forward. Okay, now if this item has a velocity, well, we'll see. Tell you what. This is how you find distance. You have to find out when your velocity is positive and negative, and you're going to treat your velocity like it's the velocity, like it is a derivative, and we're going to find critical points. So I'm going to set that equal to 0. 0 is going to equal 2t minus 1 plus 1. So I'm going to subtract 1. Subtract 1. Negative 1 equals 2t. Divide by 2, and t is going to equal negative 1 over 2. Now I have to make a sign chart, so that is a critical point, CP. Now I'm going to make a sign chart using that negative 1/2. Now, you might be thinking, what is he doing? It's negative. Why is he doing a negative? He's doing it wrong. He's doing it wrong. He's doing it wrong. Just watch. Just watch. Please. Just watch. If I plug in 0 into the velocity function, I get positive. And if I plug in like negative 10, I get negative. Now, I only care about positive values. So no matter what, this guy's velocity is always positive. So nothing's going to change. If the velocity is always positive, then the integral that we set up is going to be the integral between 0 and 5 of 2t plus 1 dt, which we already did. It's 30. So since this guy is always moving forward in our specific problem, we're not going to have any difference between displacement and distance. So if I throw a ball forward, if this thing drives forward, right, and all it does is drive forward 30 meters, then it traveled 30 meters, and it's 30 meters from where we started. Again, what we're trying to do, the difference between displacement and distance is distance would be if I go back 10 feet and forward 10 feet, I may have traveled 30 total feet, but my displacement is 10. So in this one case, the displacement and the distance are exactly the same. I can go the distance. Up there goes another copyright. I'm not going to make money off of this thing. That's for darn sure. Even if I didn't sing songs, I wouldn't make money off of this thing. All right, there's our velocity. I care about what's going on between 3 and 6. I want displacement and distance, and it's feet per second. All right. So let's start out with displacement. Integral between 3 and 6 of 3t squared plus 10t minus 5 dt. That's going to become t cubed plus 5t squared minus 5t. Limits are 6 and 3. Six cubed plus 5 6 squared minus 5 times 6 minus 3 cubed plus 5 3 squared minus 5 times 3. 6 cubed plus 5 times 6 squared minus 30.
The answer is 366.
3 squared plus 5 times 9 minus 15.
The answer is 39.
366 minus 39.
It's 327.
And in this case, it was feet. Distance. All right, so I want to just barely see that. I want to barely see it. All right. So to find my critical points, I'm going to set that guy equal to 0. Can I factor it? Oh, please, Lord, let me be able to factor it. So one of them has to be 3t, one of them has to be regular t, one of them has to be positive, one of them has to be negative. So if I make this positive 5 and this minus 1, I think that'll do it. 3t squared plus 15t minus, no, that didn't do it. Or did it? I think I have to do I have to do quadratic formula. Alright. Alright. So t equals negative b, which is negative 10, plus or minus the square root of b squared, which is 10 squared, minus 4 times a times c, so minus 4 times 3 times 5.
It's 60.
All over 2a, which is all over 6. Square root of 160.
The square root of 160 is approximately 12.6491.
All over 6. So my options are this. Negative 10 plus 12.6491.
The answer is 2.6491.
2.6491 divided by 6.
The answer is about 0.4415.
Okay. I'm not going to try the other one, because it's going to be a negative minus a number divided by 6, and it's going to give me a negative time, and I'm not supposed to have negative time. So I'm going to make my sign chart using 0.4415, and I'm going to use 0 and 10 to plug in, and I'm plugging it into the velocity function, which is right there. And if I plug in 0, I would get a negative number, and if I plug in 10, I would get a positive number. And so this is what I have to do. I have to find two integrals, okay, and then add those integrals up. So I care about, wait a minute. Oh, God is good. Look, I am just kidding. I only care about what's going on between 3 and 6. Huh. So who cares about this mess? Pfft. I don't. Which means, if I went from 3 to 6, it's always going to be moving forward again from 3 to 6. My distance and my displacement are once again the same thing. Well, I'll tell you what. I felt super sad going into this problem, and I'm ending it super happy. Great. Ugh. Whew. And see that little shaded down arrow? We're done. Oh, man. So exciting. Well, this was the Calculus 1 crash course. I feel like I need to crash into a bed because it's 9:30 p.m. Eastern Standard Time. God bless. May your days be merry and bright. Adieu.